Before we start on the actual problem, I'd like to point out a little bit of cultural hypocrisy, if I can. This all started because I put this video together in February of 2015, and as I did that, I took out the salt container and a pot and a couple other things from the cabinets to use as sort of visual aids for this lecture, and you'll see some of them as we go along. But around that same time, as it does every year, the Sports Illustrated swimsuit issue comes out, and there was a great controversy as to whether that cover was a bit on the too revealing side. And I'm having that in my ear as it's covered on the news stations while I'm looking at this particular container of salt, and I'm thinking, there's a bit of a double standard here. So let's put them side by side. One of these is too revealing and the other is not. One of them's an adult, at least. The other one is supposed to be a child, but it doesn't really look like it if you look at the Morton Company's history, because then originally the logo was much more obviously childlike. And it has sort of evolved into this sort of indeterminate aged figure with a raincoat covering very little from the leg area. So to me, this is just a good wind away from Marilyn Monroe's famous pose over a subway grate. It leaves nothing to the imagination. Again, one of these is an adult. The other is supposed to be a child, which is a little disturbing. So, just in the interest of not containing the double standard, I think that logo probably belongs something a little bit more appropriate. Instead of on the Morton salt container, I think it would be more appropriate to put it here on the Parisa body sugar container, like so. So, with that, let's move on with the lecture. All right, with that out of the way, we can start looking at the real numbers. Say we take the standard 4-quart pot, we fill it about halfway up with water.
Heat in the kitchen, pot on the stove, water getting boiled.
So 2 quarts times the conversion factor liters to quarts times the rough density for water, and we end up with an amount of water in, surprise, surprise, kilogram terms, which is what we need it for here. Then let's say we're gonna put in a little salt. Just to give us a round number, I'm going to say about 5 grams. For most people, that's probably about 5 to 10 times what they would actually use if they were cooking pasta, but just to give us a number to work with, we need that in mole terms because our molality concentration, our concentration in moles per kilogram of solvent, is the solute, in this case sodium chloride, is in moles, so we have a mole amount for that. And from there, we can put that plus the mass of water in kilograms into our molality formula, get the concentration in those terms. So that's where we have to start. So we do that, not particularly difficult. Then we have our boiling point change formula, very similar to the freezing point one that we did in person, but we're going to have a different value for K because we're talking about a different physical change. We're talking about boiling instead of freezing. In this case, we're going to have an I that is not 1 because we're not talking about something that's covalent. Since sodium chloride is 2 ions in solution, then I here is 2. And we have our molality concentration from the previous step, so we can actually put all this together and start actually making some dinner. We put all this in place, so we end up with 2 times the boiling point constant for water, which is 0.512 degrees C per molal, times our molality concentration that we worked out in the previous step. And what happens? Well, not much. We end up with a change of 0.0463 degrees C. Does that make any sense? Well, sort of. So let's continue. Our boiling point change is the original boiling point for water without salt in it, which is 100 degrees C at 1 atmosphere of pressure. We add that 0.0463, and remember, the significant figure rules say that you have to limit your answer to the least number of decimal places, which in this case is our original 100.0 degrees C, which means in significant figure terms we haven't changed things at all. Our change is insignificant. So, what does that mean? Everyone does this. Everyone knows you're supposed to add salt to the water before you cook pasta because it supposedly makes it cook faster. The reality is, no, it doesn't. So, why don't we try something which I admit that I'm actually very, very bad at in life, and that is, why don't we try looking at the instructions? It might actually teach us something here. So, we'll turn the box around, have a look at the instructions, and surprise, surprise, look what it says. Add salt to taste. That's what you're adding the salt for. If you've ever made pasta without salt in the water, you know that it tastes disgusting when you're sampling it to see if it's actually done. Salting the water actually gives you something that has a little bit of flavor to it so that it's not so unpleasant to actually check it. So, but let's say that we're still a little on the impatient side. Patience, as I say, is a virtue, but it's a virtue for people with nothing else to do. I'm hungry now, I want to cook things faster, so let's have a look at what it would take to actually get the job done a little quicker. So here's the reverse calculation, where we're going to say that I want a 10-degree hotter boiling point, arbitrarily chosen, but that should speed up the cooking a little bit. K and I are still the same. The mass of water is still the same. The molar mass of sodium chloride is still the same. So we're actually solving, instead of delta T, which we did in the first part, we're solving for that mass of sodium chloride now. So we have to rearrange the equation a little bit. You can do this before or after you put the numbers in place. I've already put the numbers in place there, but here's what it looks like without them. So I'm just rearranging the entire equation, shown here, to get to the mass over the molar mass of sodium chloride with everything else on the other side. Then we shuffle it one more time, getting the molar mass over to the side with all the variables, and we have just the mass of sodium chloride left on one side. So if I do that, and now putting all the numbers in for the variables, the 10 degrees C change, the mass of the water, the molar mass for sodium chloride, I, which has no units, and the boiling constant, which is in degrees C per molal units, I can work out how much sodium chloride I need to bring the temperature of the boiling water up by about 10 degrees. So if I do that, look what I get. Okay, so I get 1,079.86 grams, or roughly a little over a kilogram of salt, or 2 1/3 pounds of salt. That translates, by way of splitting it to the elements, to about 425 grams of sodium, which is about 185 days worth of your USRDA, your recommended daily allowance, which is 2.3 grams a day. So this would top even eating at McDonald's or, KFC in terms of unhealthy sodium content. This would put them to shame. So not exactly a great idea. So occasionally, patience really is a virtue, and we're going to have to just wait a little while to get things cooked. Otherwise, we're going to die from a heart attack pretty quickly. So keep that in mind while you're making dinner, and we'll continue with this next time.